what it is, and then we'll look at quite a few examples. GPars is essentially a concurrency library. We often want to write multi-threaded code. So if you're going to write code that involves multiple threads, how do we go about launching threads? Well, when Java came out, we had a consistent library to create threads, but then soon we realized that it was at a level where it requires a lot of time and effort to manage the threads itself. And it would be nice to have a higher level of abstraction that removes a lot of burdens from our shoulders. What GPars does is it brings a number of things together that we have been used to in other languages for over the past few years at least. For example, Erlang introduced the concept of actors, and then Scala brought in the concept of actors onto the JVM. But of course, if you're using actors or Akka, you could do that from within Java code, from Scala code, from Groovy code, but none of that is going to give you the Groovy fluency. So if you're programming in Groovy, then you want a little bit of idioms that you're used to in the Groovy language itself. So GPars is a library that's written to bring some of those concepts on, not just the actors, but a few other things we will see here. So when would you be interested in GPars? The very first thing is you would be interested in GPars predominantly if you're going to be programming in Groovy. If you're not programming in Groovy, you could still use it, but you're not going to get the real benefits out of the fluency that GPars really offers. So GPars is really a higher level of abstraction. It brings a wealth of things. We're going to look at what it brings. It is a library written in Java, but it's written with the intention of using it from within Groovy to really benefit from the Groovy fluencies, the Groovy capabilities, and things like that. So we're going to take a look at quite a number of things we can do with GPars. First of all, let's talk about creating threads. Without using GPars, let's spend a minute talking about how you could use threads within Groovy itself. It already offers certain very interesting capabilities, if you will. Creating thread in Java requires creating a new thread object. Of course, then you can call start on it. But in more so recent times, you would be using things like executor services. But if you're going to use something like a thread, Groovy already makes things a little bit easier. For example, thread, you could simply pass to a thread object a runnable. So if I were to run this like it is Java, for example, you would write runnable over here, and then you would implement, for example, the method which is a public void, let's say run, and then you would implement within this method whatever you want to do. For example, I'm going to say running, which would be running in a separate thread. And then you can, of course, call start on this to get this thread started. You would put all the semicolons, mains, and all of that around it, and eventually that's the code you would be running, isn't it? Now, this is a way that you can write code in Groovy as well, but Groovy offers a lot of support to reduce the amount of code you have to write. So notice here, this is like you would do in Java. Like I said, you add a semicolon, a main, and stuff like that. But you don't have to go through that much effort at all. In fact, the essential part of it is the code you want to run in a thread. So you can just trickle it down all the way to it. For example, I can just create a thread here, and to this I can pass just a closure, and the closure itself can say just run the thread, and you can start reducing the amount of code you have to write in Groovy. So it doesn't take a whole lot of effort to write code in Groovy already because it removes a lot of ceremonies. However, if you really want to do quite a bit of multi-threading, we already know that we shouldn't be using thread class. We want to use executor services, because executor services gives us a thread pool, and then we can run things on a pool of threads. It is much more civilized, more sensitive resource, and so on. But how do you really use executor service? Well, we could use the JDK library to do that, but that requires quite a bit of effort and time and work. GPars kind of fills in the gap really well. So let's look at what GPars provides. First of all, GPars provides certain interesting functions, but rather than providing separate functions to do things, they did something pretty clever. GPars makes use of Groovy metaprogramming. Metaprogramming allows you to inject methods into existing classes, and in this case, they decided to inject certain methods into closures. So if you're familiar with Groovy, a closure basically is an anonymous function. For example, I could say closure equals, and here is an example of a closure which says, say hi, And you could even pass a name here. For example, you could say, hi, and then a name, and then I could pass the name over here, for instance, right? So in this case, of course, I could call this closure, and then I could say over here, hi, and it can use that. So it's a little anonymous block of code. That's what you're using. Well, what you could do is you can use the closures, and closures basically are injected with a certain methods in GPars, by GPars. So the minute you use a with pool, you have certain added benefits. To understand this, let's take a little example. Let's say we want to organize a party. Of course, to organize a party, you need to get some food, you need to get some drinks, and you cannot start a party until you get it. So I'm going to have a get drink method, and let's simply say, getting drink over here. And let's say for a minute that getting drink is going to take a certain amount of time. So we'll say thread.sleep, and let's say it takes about 2 seconds to get this. And once we do that, we also have a method, let's say get pizza, and we want to get the pizza before we start the party. So we'll say getting pizza again, and then let's say this takes a bit of time as well. So we'll say this takes about 2 seconds of time as well. And when we are done, we'll say pizza is here. So that's the return value from this function. So how would this look like? So I'm going to say time.code, where time is a little helper class I've written here, which is going to tell me how much time it takes to run a piece of code. So all that I'm going to do is I'm going to say time code, and I'm going to get drink over here, and I'm also going to get pizza, and I'm going to print the result of this. So we could even print it outside, or we can just print it right here for now. So how much time is this going to take? That's a sequential code, right? We can already see how much time it's going to take. This one, of course, is going to take, in this particular case, is going to take about 2 seconds of time. And the reason, of course, is because I'm going to call these two methods that I have here within this code. I need to see where the error is coming from here. So give me a second. So I've got some setup issue. Oh, def, did I do that? There we go. This is def. How did that become a get? Thank you. So let's go ahead and try that. So you can see that this code is getting the drink. It's getting the pizza. You expended about 4 seconds to get this, right? Now, that's kind of obvious because get drink takes 2 seconds, get pizza takes 2 seconds, give or take, so that's about 4 seconds. Now, obviously, in a world we live in, people are very impatient. They're not going to wait for your party to start that long, right? So you want to make this faster. So why don't we concurrently go get drink and get pizza at the same time so we can get the party started soon, right? So how would we do that? So we could call one of our friends and say, why don't you get pizza while I go get the drink? And when both of us come back, we can continue. So to do this, I'm going to use GPars over here. So how would it look like? Well, I'm going to bring in the GPars library, first of all. So bring in GPars. And GPars has a pool. I can think of this pool as a wrapper or abstraction around the thread pool. And then I'm going to run this with the with pool command. Now, remember that this took about 2 seconds plus 2 seconds, which is about 4 seconds to run. But let's see how we can run this more concurrently. So I'm going to put this into a with pool block of code. The with pool basically says that I'm going to run this within the context of the with pool, meaning make use of the thread pool that's available for us to use. So in this case, I'm going to create a closure, a very simple block of code. And within this block of code, I'm going to go ahead and call get pizza. So get pizza is going to go get the pizza, but I'm going to wrap this into a closure and call async on it. So the minute I call async, it's going to start executing in an asynchronous call, and it's going to give to us a future object. So we could save this into a future object, and we could say, for example, future equals. So what that means is, it says, I'm going to go run this in a separate thread, but obviously you need the results of this execution at some point. So we'll give you a future object, which will eventually hold the result that comes back. And then when the result is done, you can get the value from the future object. Well, in order to use this, I have to first of all go to the future object and do a get on it to get the data. And so this involves a few extra steps of calls, and that can become a little annoying because you got to get the future object, and then you got to call a method on the future, then you got to block on the result, and then you got to call a get on it. Seems like that's not very groovy, because in Groovy we don't do all those different steps. To minimize that effort, we can simply replace this with result itself, and then we call it as call async. So call async basically says, go ahead and do this asynchronously. When you're done with it, just give me the result back. You can call the get on this one and do it, get the result. We're going to call the get drink over here. Why? Because after all, you don't need several threads. While the other thread is doing the work, what are you going to do, right? You might as well go do some work as well. So you can go ahead and call the get drink method over here. And then when you come back from getting the drink, you could print the result that you get back from this call and say what the value is. So what time is it going to take? Well, let's go ahead and wrap this into time.code one more time so we can see how much time this is going to take. So we'll just wrap that into it. So I'm using a closure again to just measure the duration of time itself so we can easily look at how much time it takes to go about doing these work. And how is that going to work? So let's go ahead and give that a try. So this time, of course, I'm doing a call async method. So call async is what I want to use. So let's make sure I'm using this properly here. So call async. And what does this do? This launches one thread to get the pizza. And then the other thread, of course, gets the drink. Notice the sequence of printing here, which is kind of unpredictable, right? Because they're running concurrently. So I call get pizza first. I call get drink. They both got printed, but the order, of course, is pretty non-deterministic because of concurrency. But notice this time we only took 2 seconds, not 4 seconds to run. So launching this thread was pretty simple. We just delegated this to another thread and then said, so what is it going to do? This starts in a separate thread. Then we execute this in the current thread. Then we're going to block on the current thread until the result comes back. Now, let's think of a certain problem we're going to have. Now, if I'm going to have this done in a separate thread, then I need to wait for this other thread to complete. But any time, by the way, you wait on a thread, there is a danger. What's the danger? That it never comes back. And he said it may never come back because if I give him the money and say, go get pizza, he's probably going to take the money, go get the pizza, eat and go away, right? And one day I find him, it's like, hey, I gave you the money for pizza. Oh, that was a great pizza, by the way. Thank you, right? So here I'll be waiting. So giving money to him, I better also combine it with the timeout, right? After a certain time, if I don't get the money, I better move on to doing other things. I'll deal a process not completing or a task not completing within a reasonable amount of time, you can deal with it gracefully. So all that we saw is some syntax sugar and convenience methods that Groovy GPars added on top of the closures themselves. So you can see the very lightweightedness and fluency of this in a way that you are doing metaprogramming injection. So GPars really injects these methods into the closure, and within that context you have this available within the with pool. If I try this code outside of the with pool, I'll get an error because those methods are not available outside of this context. So we looked at a very simple, anywhere you want to use just a little, very lightweight, go and do this task on a separate thread and come back kind of an operation, you can use that. But we learned from exercises from Erlang and also from Scala and Akka that we could actually use this concept of actors. So what is an actor? An actor is a task that runs on a single thread. And one of the reasons to use an actor is we really cannot deal with shared mutability in code properly. Because when you take a variable, if you make a variable mutable, we already have a few problems. There are errors that could creep in. But the minute you take a mutable variable and you have multiple threads using it, it's really hard to write code that's correct and easy to maintain. And we get into enormous amount of problems. I like to call this as the synchronize and suffer model, where it really becomes problematic to maintain this code. So there are two ways to deal with this problem. One way to deal with mutability is to do what is called basically managed immutability, going along the lines of what Clojure does in terms of having software transactional memory, and it allows you to mutate variables, but you control the mutation within a set of transactions that are running. An alternate way is to remove the shared mutability, but you still have to mutate stuff most of the time if our programming model is Java-like. So how do we deal with it? Well, one way is to use what is called isolated mutability. Isolated mutability means that a variable is mutable, but no two threads will ever be able to mutate this variable at the same time. This is governed automatically. Now, how would this work really? This is where an actor comes in. An actor always runs within a single thread. So imagine for a minute that I have a cell phone number, and I'm going to give you my cell number, and let's say you can call me anytime, and anybody else in this room can call me at any time also. And obviously, if any of you call me right now, I'm not going to pick up your call because obviously I'm busy talking. So both of you, or two of you, or three of you call at the same time, and immediately you are going to be rolled over to my voicemail. And of course, all of you can leave a voicemail exactly at the same time, isn't it? Assuming you are using a good provider for the phone network, you all can leave a message at exactly the same time. Now, of course, you are going to leave a message and walk away. This is called a fire and forget model. And once you leave a message, you all are on different threads by yourself. You leave a message. When I finish my meeting, I go check my voicemail. It tells me there are a few messages. Oh, that's been a busy day. I'm going to listen to messages. So I'm going to start listening to messages. How many messages am I going to listen to at any one time? Only one, even though I have 2 ears, right? Why? Because I'm still single-threaded. I'm going to take one message. Either I'm going to work on it, or I will delegate it, and then I'll go on to the next message. So in other words, now you understand what an actor-based model is. An actor has a message queue, and messages can be dropped into the queue concurrently from multiple threads, and they're all non-blocking. They just drop a message and move on. The actor itself is notified with messages in the queue, and only one message at a time is processed. So if any variable I maintain on my side is going to be single-threaded variable, because I only process one message at a time anytime, so I'm going to pull one message at a time and work on it. So even though this variable is mutable, it is isolated from multiple threads. So in other words, you don't have to work extra hard for thread safety. Thread safety is automatically guaranteed in an actor-based model. So this is what is provided by frameworks like, libraries like Akka. Erlang also provides this through processes. And Scala has, those implementation. But what if you're programming in Groovy? You can certainly reach into Akka and use this from Groovy as well. But if you want to enjoy the Groovy fluency, you could use GPars and actors through it. So let's look at an example of using actors through GPars. So how would this look like? So I'm going to start with a default actor, which is the name of an actor class from which you can inherit in Groovy. So let's get started with a simple class here. So we'll start with, first of all, a default actor. So what kind of actor am I going to create? Well, we will create a little actor. We'll call it let's call it Bollywood actor, right? I really don't have a clue who actors are these days, by the way, so I'm quite at a loss. So you need to help me with some names here. But this is going to extend from default actor, right? So in this case, of course, this is a Bollywood actor. Actually, my children know more Bollywood actors than I do because I don't watch movies, but they do all the time. So in this case, of course, I created an actor. What does the actor provide, really? Well, the actor is going to provide an act method because that's what you're going to ask the actor to do, right? So I'm going to define a method here called act, and it doesn't return anything, but what it does, it does a loop, and the loop is going to continuously be repeating. And within the loop, I'm going to have a react method. And within the react method is where I'm going to get a role that this actor is going to act. And then we could simply print out here acting the role, and then we could just simply say role. So you can see how I implemented an actor object. Now, obviously, in your programming project, you wouldn't be writing Bollywood actor unless you're writing something in the film industry. This would be a message processor, a print processor, what have you. And you would write that class and extend it from default actor, but you would be writing the loop very similar to this. Now, when you look at this code, it's a little bit confusing because you look at this loop and say, hey, what's the loop doing? The loop is taking a closure. You're calling into the loop, and that calls into a react. But the minute you hit the react, the thread that calls react will suspend and go on to do other things. So the thread is not going to block and wait. It'll go on to do other things. And when a message arrives into the message queue, a thread will be assigned to run from where you left on the react until it loops back and hits the react again. It'll release the thread and go back and wait. So in this case, as you can see, we're just printing acting the role of, and then we are just printing the role here, right? Let's go ahead and use this. So first of all, I'm going to create an actor here. So who's your favorite actor? What was that? Akshay. Okay. Has to be a good one. You like him. So in this case, new, we create it. We can give a name here, right? So we could say a Bollywood actor. We can give a name. And we could say the name. So we'll just say name here equals. And let's assign the name as well. So give a name for the actor. So let's receive a little name field in the constructor. So let's go ahead and write the information here, right? So let's go ahead and give a name. So how does this look like? So the minute we create it, we're going to start, right? This really starts the message loop, if you will. Unless you call start, the message loop is not going to start. So in this case, of course, the minute we create, we want to send messages to this particular actor. So we could send some roles. What's the role? What's the role that you like that he played? Rowdy. Very noble role. Okay. So we can call that, and of course we have to wait on this also, right? So we're going to say dot join, and how long are we going to join? Well, we're going to join for, let's say, 1 second, give him a time, and we could say in this case java.util.concurrent, kind of scary to use that, but the essential point here is just to give a time unit. So time unit dot seconds. So essentially what we are saying here is we're going to create this actor, start the message loop, and push a message on the actor. Now I'm using the shift operator in this case, but you can use other methods as well, and then you're just posting this message. Now what is not very clear when you look at this code is, how is the sequence of things happening? Well, when you look at line number 16, in line number 16, you're on the main thread, but when you send the message, you are going to jump to another thread, and automatically goes to yet another thread where this is going to run, and then it's going to process the message on the other thread. So you don't have to manage the threads yourself. The thread management is already baked in. And as a result, you can simply use this fairly easily without having to put too much time and effort into this. So let's go ahead and see how this is going to work in this particular case. Oh, I made a mistake here. So this is going to be in the no such property class name, of course. So where did I put the name over here? I forgot to define the field called name, didn't I? Let's define the name field. So what's happening in this case? He's playing the role that you desire so well, right? So, but what's going on in this case? He did print the message, but that doesn't quite give us the full picture. To understand what's going on, let's go back and do one more thing. Let's go ahead and print out here thread in the main, right? So we'll say main, and then we will say in this case, this is going to be thread.current thread, and then we'll just ask him to print the current thread information. Now that should be no surprise. It said it's thread main thread. But let's go back to this code and say acting the role of in thread, and let's go ahead and say thread.current thread over here also. Now notice in this case, when we run this, the main is running in the main thread, but on the other hand, the role is being played by actor thread 1. So you can clearly see how it jumped threads automatically. So we didn't have to write explicit code to do thread jumping, but by default, by nature, actors run in a separate thread. And as a result, the main is in the main thread, but on the other hand, when you did call the actor says, I'm not in main thread, I'm running in actor thread 1. You could send multiple messages to this actor concurrently. So for example, if I go back to this code, just to simulate a behavior here, let's go ahead and put a little thread.sleep, assuming that this actor does take a little bit of time to play this role, a second delay. But in the meantime, let's go ahead and select another role for him. Do you have another role for him? What an improvement. Okay, so in this case, of course, we're going to play another role, right? But we push two messages on it at the same time, right? So I'm actually very scared to ask him his next role, because he's going to say a rowdy scientist, which is very dangerous, by the way, right? Which puts nuclear arms in his blood. So I won't even go there anymore. So what you see up here is, notice one thing though, but in this particular case, we have sent two messages to this actor, but on the other hand, even though we send two messages, both these messages are happening in exactly the same thread. So the reason for that is, our actor is single-threaded, and so the actor can only play one role at a time, and as a result, you have the main thread running the main code, which is pushing these messages and walking away. It's a fire and forget. You're not waiting for these to be done. So if you go back and look at the main itself, I could say over here something like, role 1 requested, let's say, and then we'll say role 2 requested. But you can see that these are fire and forget. So when you run this, you can see that the roles were requested already in the main. But the actor has not responded yet. You queued up a set of requests, and then of course the actor kind of pulls one request at a time and ends up playing it. So we saw how we could write this and easily dispatch messages. So it looks like we have a nice actor engine going through. However, there is still one problem we have to deal with. In this particular example, it was fairly simple. We simply sent one type of message, which was just a string, and that was kind of fairly simple. Let's take this a little bit further to a trader. Now this trader, of course, is going to help us to trade. So I'm going to say over here, the trade itself I want to take. But what kind of trade do I want to do? Let's say for a minute I have table in here. And which is a good idea, by the way. I'm making this immutable for two reasons. One is because I'm lazy. I don't want to write the constructor for it. But also, because of thread safety, you want to make sure that the messages you pass between the actor and the other threads are actually immutable. Because if you pass mutable objects, you may compromise thread safety potentially by trying to alter things. So it's not a bad idea to use immutable in this case. So the way to handle this would be to make that immutable. And similarly, of course, I need another actor in this case another message object. Let's say in this case, a buy is the next thing I want to do. So my trader is going to process these. Maybe there's a different way to process each of these. So I'm going to do something really ugly. I'm going to say if trade instance of a buy, then I would say, let's say buying, and then I could display the details of the buy trade itself. On the other hand, if the object is going to be, let's say a sell trade, I would then say instance of sell, and then I could specify that I'm going to sell it, and then specify the sale. We could still use this, of course. We could say, trader, and then create the trader object, and then we could ask him to do a few trades. We could say trader, and we could ask him to buy maybe a few Google stocks. So we could say, buy me 100 Google stocks. Or we could say trader, and then we could say ask him to sell maybe a few Apple shares, and we could ask him to sell 10 Apple shares. We could ask him to run through some of these exercises, and of course when we are done we want to still join him and then ask him to weight it. So what's the problem in this code though? The problem in this code is we are really doing a type checking. In other words, we are writing what is considered to be a procedural code. And we know that in OO programming, we can use things like polymorphism and function overloading, all those good things, right? So why not just make use of some of those features to write this particular code, rather than working through a little bit of a procedural code right here? Well, unfortunately, though, the default actor will not provide us for that. So we need to upgrade to something a little bit better, if you will, for us to be able to do that. And what would that be? Well, in order to do that, we would have to go back and use, let's fix this first. What am I doing here? Anybody sees it? So he's complaining in this case in line number 31, which is right here. So I'm giving him a buy object, so which is this buy here. So let's put a new on him because we want a new object to be brought. There we go. And let's fix the other error. So 33 now. So right there is a trader. Trader.join. All right, so how do we really distinguish from these objects? Well, it's kind of surprising, though, because oftentimes we would argue that a language like Groovy is dynamically typed, and so you would not expect much of type information to play a role. So what I'm going to show you is quite ironic. We're going to use overloading. But how could overloading work in a situation like this? The reason overloading works in a situation like this is Groovy has an interesting feature called multi-methods. Not many languages support multi-methods. Multi-method is a form in which the method can be dispatched based on not only the type of the parameter, a target, but also the type of the parameters, if you will. Let's think about this a little bit further. What is polymorphism? Polymorphism says, go ahead and call a method on an object, but the method you call is dispatched based on the type of the object and not the type of the reference. Well, multi-methods is polymorphism on steroids. The method you call is not only based on the type of the object on which you call the method, but also the type of the parameters you pass to it. So Groovy supports multi-methods, Clojure supports multi-methods. Not too many languages support it. For example, Ruby doesn't. But I'm going to leverage multi-methods over here. So notice what I'm going to do here. I'm going to replace this with the dynamic dispatch actor. So I'm going to trade the default actor to dynamic dispatch actor. So I'm going to inherit from this class. And as a bonus to doing it, I can now get rid of this function here. And I can simply write on message. And I can say if it's a buy operation. And then I'm going to say trade. And in this case, I'm going to simply say that I'm interested in buying. So I'm going to just display this information right here. So as you can see. On the other hand, I'm going to also write an on message. And this could be a sell operation. Again, a trade. And in this case, of course, I could say that I'm selling in this case because that's the operation I want to perform. So notice that I just overloaded these two, the two instances of on message. And that's all I did to get around this, right? So it reduces the amount of code you have to write. You don't have to do type checking anymore. But the beauty of this is you can start writing special message handlers depending on the type of the object you are getting, right? You can't really do this, and surprisingly, you cannot actually do this in Scala, even though it's strongly typed. And the reason is because a message coming in is just an object. And you don't have multi-methods, and it really becomes problematic. You got to kind of do the dispatching. Whereas because of multi-methods, Groovy is able to handle this here fairly well. And that's what we are leveraging. So we don't have to do type checking in the code anymore by switching over to the default dispatcher. So that we saw how we could upgrade to it. We could continue to use actors and do other fancy things with it. But I want to switch over to talk about something else that GPars supports. This is a concept that's fairly old, relatively speaking, but not too often used because it's kind of fallen out of flavor. But if you really look at conceptually, this is an extremely exciting concept, a data flow. This really goes back to late 70s to early 80s when there was excitement around the so-called Manchester machines, which were also called as data flow computers. And data flow architectures were kind of a fancy thing back in time. People were getting excited about this, especially academics and researchers were excited about this. Because what a data flow computer would do is it would give you absolute parallelism. Because the way a data flow computer works is you think about all your computations as nodes. Think of these as random balls that are floating around. And anytime a node is ready for computation, it can run if a computing processing unit is available. But for a node to be ready for computation, you don't have to go call the node. Nodes are kind of active. And a node says, as soon as I have all the input I depend on ready, I am ready for computation. So think of an object graph or think of a graph of computation where you have an input coming in, going to a node, and the results of those nodes are going into another node, and then the results of that going further. When you have a certain node, a node is ready to run as soon as the inputs arrive for it. And so you're not sitting there and sequentially scheduling instructions to run. Instructions kind of are hyperactive. They kind of float around, and as soon as things are ready for them, they sign up to run. And as soon as the processing power is available, they are ready to run. So this gives ultimate concurrency in applications. Well, unfortunately though, while this was a very interesting concept, it really never took off. There is no practical data flow machine in the world today. Partly the reason for that is, how do you program this stuff? Right? The hardware can give you the power to execute. Instruction at the architecture level can give you the power to execute. But how do you write code to make use of it? So general purpose computing stops at a certain level, and going from sequential to parallel code is not that obvious at all. We're still struggling with that in our field. We are learning about a lot of things as we do. So that kind of went out of flavor along the way, and we don't have any way to really use those machines. But that doesn't mean the data flow concept itself is a bad concept. The contrary, it's actually a very powerful concept. But we're going to use data flow here to simulate such a behavior. Now imagine for a minute that you want to perform some concurrent task, and you want to make sure those tasks run. What do we normally do? You already saw me do this actually. You would schedule a couple of tasks, but then you do a join on them. And then you wait for them to complete before you continue. But rather than waiting on a task to complete, why not wait for a result to arrive? So think of this as a data flow variable. A data flow variable has only one option to bind. In other words, think about this as a set once variable. You can only set the value of a data flow variable only once. If you try to set a value more than once, you'll get an error. So it's a set once variable. But the minute you set a value into it, you can read the value any number of times from it. But on the other hand, if the value has not been set already, meaning the value has not been bound, you are called to request for the object, value will block your thread. So this gives a very convenient way to do things. Why? You have a computation you want to perform, bind it to a data flow variable, go about doing your own stuff. And when you're ready for the result, come and call a get on it. If the result is not ready, you're going to block and wait. But by the time you come back, if the result is already done, your get is non-blocking, you immediately get the data and you can move on, right? So this becomes very easy to work with. Let's look at an example of how we would use this in the code. So what I'm going to do here is to bring in a data flow variable, but I'm also going to bring in a task that I want to use as well. So let's go ahead and import these two guys here. So we'll bring in an import of these two. But I need a little function to work with it. So we'll call it as getData. And this is going to take a URL string for which I'm going to get the data for. So I would simply say here, let's say for instance, I'm going to just say getting data from, and let's say URL string. And we will also print received. So we'll simply say received data from, and then we'll put the URL string. So we can kind of see that the data request is completed. And we'll put the data itself, will return it. Now what is this data that I'm interested in returning? Well, the data itself is going to come from the URL string. Groovy makes life very easy to do this. Simply call a URL and call a toString on it, or rather a text on it, and that gives you the data from this. Let's see if that's actually working. Let's first print out a get data over here. So let's go get the data from, let's say URL1, where I'll say URL1 is, let's say HTTP, and we'll simply provide a Google over here, right? So this is going to go get the data and put some stuff out. So this is going to be a simple execution of the data itself that I'm interested in. Well, let's see, look at the URL here, to URL, and then of course ask him to get the data. That's data from Google, right? Fairly simple. But let's also define one more data here. So let's say URL2, and let's go ahead and change that to another address here. So I want to get another input. So we could use these two. But what if I want to get the data from both of those? So time code, and let's go ahead and say URL1. So we'll say get data from URL1. And we will ask for the size of the data. And then we'll say plus get data from URL2. And this time, of course, let's get the data for the size. And I want to print the size of the data from these two URLs. Now, of course, this is going to be a sequential execution of the code, isn't it? And that says it took us about 15,523 seconds to run it. That's actually a large number. That's a data rather, right? Not the time. 1 second, pardon me. Well, let's kind of delay this a little bit so we can actually see this a little bit more. So let's put a little sleep here so it becomes very evident so that we don't have to rely on the network alone. So that's about 2 seconds, right? It should take about 2 seconds because we're doing this sequentially. And then the data is displaying. Of course, the data size would differ based on what we are trying to do. That shows about 6 seconds. But how do I make this concurrent? We already saw examples of making this concurrent. We could use async, for example. But what if we can just bind this to a data flow variable? That would be a different way to look at it, isn't it? So notice what I'm going to do this time. Rather than calling these two sequentially, I'm going to go back in here and define a task. Now, before I define the task, let's go ahead and define a variable. We'll call it as URL1 data equals new, and we'll create a data flow variable. And URL2 data equals, and we'll define a data flow variable. So these two data flow variables are unbounded at this time, right? They're not tied to a result yet. But then within the task 1, I'm going to say URL data 1 is going to be, and I'm going to go get the data for the URL 1 in this case. Similarly, I'll write a task. This is going to get the data 2, and that's going to come from URL 2 in this case. So I simply unleashed 2 threads and said, you guys go get the data for me. But then my life becomes very easy. I'll just print URL 1 data and then dot value dot size. and then plus URL2 data dot value dot size. So essentially I'm telling him to go get the data. But the difference here is it's going to unleash those two threads for us concurrently, and then it's going to block on the size, call to the size method, because the val is not ready. But once it blocks on one, it's not going to block on the other if it's already ready. As soon as it gets the value, it can move on. So the data flow variables can give us this ability to schedule tasks to run concurrently and get the results along the way. That becomes very easy to work with. As you can see here, it didn't take a whole lot of effort at all. Rather than taking the 6 seconds it took a little bit earlier, it only took about 1.6 seconds here because those two are being done concurrently. In fact, you can already see this, right? Because both the gets were called concurrently, and then the received data is coming back. And in fact, you can see that the response is very different, which is kind of obvious because Google's site obviously is more efficient than my site because it's been cached several times over. And so you can see that even though that came back very quickly, and then mine came back afterwards. So that is an example of how you could use a data flow variable to write stuff. So where would you use a data flow variable? That is something you would use if you have concurrent computations to perform, but you want the pure nature of the dependency of the expressions to take care of concurrency rather than artificially scheduling these things in your code. So that becomes a lot more easier to express it. Going back into some of the things you can do in Groovy itself, there are some very interesting parallel collections available. Now this is something that I'm beginning to appreciate a lot more here, is that with collections you have data, and oftentimes you have a certain operation you want to perform on individual elements in a collection. Now one way to deal with this would be to take a collection and start creating threads and managing the data and the operations with these threads. But what if you can turn this around a little bit and say, hey collection, why don't you execute your operations concurrently for each of the elements so that we don't have to sit there and write these threads and manage it? In other words, what if the collections become concurrent collections, meaning parallel collections? Don't confuse this with concurrent collections in Java, because concurrent collections in Java pretty much, at least pre-Java 8, really support concurrency. But the elements don't get processed concurrently by itself. In here we are saying a collection actually can process elements concurrently in managing threads under the covers. There are actually a couple of different ways to do this in Groovy. Let's look at a couple of different options available to us. The first one here is called a parallel enhancer. The parallel enhancer basically says, I will give you an ability to call methods on the class, on the collection. You can call each, or you can call each parallel. And that would run concurrently or sequentially depending on what you call. But instead of calling those methods, you could also do, for example, a make concurrent and make sequential. A make concurrent would turn a collection into a concurrent collection. Then when you call each, it itself would run in concurrently. And then you could say make sequential, in which case it will turn into being a sequential call. Now, if you do this, each methods would become concurrent and sequential automatically. Let's, for example, say that I have a bunch of names over here. And I want to take these names, let's say a bunch of names, let's say Jack and Jill, and let's write a few more names, right? We can say we want to process these names over here. So we could say names.each, and I could print it, right? We'll say print it. Now print it could be a closure, so I'll just say print it. And this takes a name as a parameter, and I'm going to just put a delay here so we can actually see the difference. So we could say thread.sleep1, let's say 1 second, and then I could actually print the name itself. Now if I call this, of course, it's going to print these things, but we could put a little delay in here and see how much time it takes to run this. So we could say time.code. It's going to print one at a time. So this should take about 4 seconds, right? Because we have 4 different things to run in this particular case. So that may take a little longer to run. But on the other hand, what if I want to run this concurrently? Well, we could use, for example, the ability in GPars for the parallel enhancers. So once we use an enhancer, we could call, for example, make concurrent. So I'm going to go ahead and import this guy here. So this is the parallel enhancer. We could say, for instance, we want to use a make concurrent call. So on the collection itself, you would say names.make make concurrent, and this would turn the code into a concurrent mode. Notice I'm still calling the each, but the each will now run in multiple threads rather than running on individual thread. If I go this route, by the way, you could have functions under the covers that are using a collection, but I could send you a collection which runs things sequentially, or I could run code that is running concurrently. Of course, that could be a bit dangerous, though, because underlying code would have to still be dealing with hygienic updates. Otherwise, things could become a problem as well. Go ahead, please.
So in that sense, if I correctly understand, so for each element in the names, it will run each thread. So there will be 5 threads running currently.
From the pool.
In the pool.
Right.
So if that number of threads means number of elements got increased.
Yes.
So the number of threads will drop.
Nice. But there's one problem, though. You know more about this than they do because it's your problem, right? And you could say, you know what, my blocking factor is high because I'm going to talk to a web service, I'm going to wait a lot longer so I can actually have more threads and manage my code much better. So what you do in that case is, to make this work, you are going to specify the with pool method. Remember the with pool we were using so far, right? You still need the with pool. So you would say with the pool, and then within the with pool method is where you're going to do all of this code. Now, on the other hand, if you really want to control better, you would then say a number of threads in the pool, you would start specifying that right here. So you would give it as a parameter to the with pool and control it, and that's when you will get the benefit. So we could also go to more of a parallel collection and do this as well. Let's look at an example of how we would do this. So let's go back to this code itself that we were dealing with right now and see how this is going to work with. So I got a bunch of names on my hand. Let's go ahead and add one more here. And maybe I'm interested in performing a set of tasks on this. Maybe I'm interested only in names with 4 letters in it. So we could do something like this, right? We could do a collect method. So how do I get all the names with 4 letters in it? Let's give it a try first. So I could say, for example, name start. And we could use a collect method. The collect method could give me the name that it gets, and also it could return to me the number of elements in the name. So it.length, for example, right? So now I got the names and the length on my hand. From this, I could say, for example, further down, I could say that I'm interested in filtering. And what do I want to filter? So filter only names, by the way, which are, so this is the first element, right? And the second element. So 1 is equal to 4. So I'm getting the 4-lettered names. So I filtered those names. Now I could do a collect one more time. And this time I could simply return the names themselves. So this would be a pure sequential execution of this code in terms of getting the component values in this particular case, right? So how would this feel like? So in this case, of course, let's property for, there we go. Length, is it length or size, by the way? Length, right? So length. And so in this case, this is a name, so it is a name, right? It's names.collect. Is it length or a size? What was that? Find all. Oh, of course, find all. But that's not the problem yet. It's actually having problems with this guy here. So it.length, right? Because it's a string, and he's complaining that he doesn't know the length property. If you notice, he's complaining that he doesn't know what the length is. So length for the class string. So what does string have, by the way? Length or size? Size? I can never get that straight in my head. It's actually a length, not a property, but a method. I think the consistency is needed, don't you think so? I never can hold that in my head. Anyway, so right there is the names which start with 4 letters, and we're able to get it. What if this is going to take a little longer? Well, then of course, this is going to still run it sequentially, right? Well, rather than doing that, what you could do is you could use some parallel enhancers. So you could actually use a collect parallel and a find all parallel. So within this, of course, I'm going to go ahead and use the pool with pool method. So let's go ahead and bring that in. So in this case, I'm going to say import static and bring that with pool. And within the pool of threads, let's go ahead and ask him to run this as a collect a parallel. So very simply put, you can simply say collect a parallel, and you're saying I want those operations to be executed concurrently on each of the elements. So rather than looping through each element and executing, this is going to run them on all. Similarly, find all parallel, is going to run them in concurrency as well. And then when you're done with it, you could again collect parallel as well and ask him to give you the results back. So the idea behind this is that you're running these concurrently rather than sequentially, and you saw that working as well. But that's all great, but why don't we go a step further and all the way get through the MapReduce problem? So what does MapReduce really do? MapReduce says, I'm going to concurrently run all these scatter operations, and then I'm going to collect back the data and bring it together. So to understand this, let's go ahead and take a look at a slightly different example here. Let's say that I have some ticker symbols available, a bunch of stock prices, stock tickers I have on my hand. And I'm going to do this sequentially first. So I'm going to say, measure the time for this code. I want to find out which of these stock prices is highest price today. And obviously I need to know the price value for these guys, right? So what am I going to do to get the price value for these guys? Well, let's do this sequentially. So I'm going to say tickers dot, and I need to get the price value, so I can use the collect method. And what is the collect method going to do? I'm going to get the name of the stock and the price. So I'm going to return a it, which is the stock ticker symbol. I'm going to go to Yahoo Finance, by the way. And in Yahoo Finance, I'm going to say get price and for the ticker. So let's start with this first. I'm just going to print this alone for a minute. So this should give us all the stock prices and the values. You can take a look at the get price method later on if you're interested in. Now it's spinning the wheels. It's going to go to Yahoo and find the price for these things and report for these. Obviously that's going to take some time because it's going to go through, spin through and each of these values and get us the result, isn't it? Now on the other hand, once I find the stock prices, what should I do? My next step would be to filter the value, right? Or reduce it to a single value. And the value that I'm interested in is going to be the maximum value among all these set of values. But how would I get the maximum value? Well, that is going to be the reduce operation. And for the reduce operation, what I'm going to do is basically to take each of the pair of results I'm getting, compare the two values and say which one is higher, and then based on that, pass it on to the next level. In Scala, we call this the fold left, for example. You also have a reduce method available in Scala. In the case of Ruby and Groovy, you have methods like inject. And inject basically says, I'm going to start with an initial value, and then I'm going to start feeding that value in through here until I get the eventual value that I want to get out of it. Now, obviously, the internet connection here is not really that reliable, so I'm going to mark out the value to just get the results over here in our experimentation here. But once I do this, I want to reduce this. So let me go ahead and kill this guy and get this out. So in this case, of course, let's go ahead and there we go. So let me go ahead and mark up the result value itself so we don't have to rely on the connection. So I was prepared for this to fail. So here is the code I'm going to use. Just a little thread.sleep to give a simulation. And then we will just kind of return some arbitrary value. We don't care about what that value is. And then we'll return that particular value. Great. So given this value, by the way, what are we going to do to get the result back to you? So let's just return some value, right? Doesn't matter what that value is. So given this, let's go back over here and try this code. This is going to give us a collection of data back to us. And in this particular collection, the reduce method comes to play. So what does the reduce look like? The reduce is going to just combine the values together, isn't it? So to combine the values, you need to start with the dummy value to begin with, but this is just an array. So you can start with an empty name and a number value back at this. And once you start with the empty name, the reduce is going to do it. But using the parallel collection, one thing I'm not too happy with is the change in name suddenly. Rather than using collect, you're going to use a map. And rather than using the inject, of course, you're going to use the reduce, which is kind of consistent with the map reduce, but that kind of deviates from what Groovy uses under the covers, which is the normal approach like collect and inject methods and so on, right? So we want to change that. So the way this is going to look like is we're going to start with this particular, looks like this guy is stuck for some reason, not sure why. So all right, let's do this one more time. All right, so it's too many sleeps, that's why. All right, so getting back to this, This is going to be a reduce operation, so dot reduce. And what does the reduce take, by the way? The reduce is basically going to take initial value that you want to work with. So in this case, inject rather, right? So this is going to take a value, comma 0, and then of course within here, I'm going to tell him what to do with this particular operation. So this operation, of course, says give me a price value and a stock price value and return whichever value is bigger. So I could say if P, this is going to be the collection of values, right? So if the price of this guy is greater than the price of the next value, then go ahead and return this particular value itself, otherwise return the other value. So we could go ahead and start writing the code to do this. But rather than going through this, to speed up the operation, we will use a parallel collection right here. And then we would say map, you don't have to change the collect call itself, and then rather than using the inject, you would say reduce, and this basically is going to run it concurrently. So the trick here is to get the parallel object and then use the map and reduce. So you do have to change the code a little bit. So the consequence of this is you cannot reuse the same code you use under the covers for doing both of the operations. That is something you have to live with. But on the other hand, it does make the two code very distinctive from each other, and you can certainly rely upon a different syntax, which is not a bad idea if you think about the fact that it does make it very clear that one is sequential versus the other is concurrent. So that is baked in also. One thing I'm not covering here is that GPars also gives you access to STM, software transaction memory. And the way they do that is through a wrapper around a library called Multiverse, which is a Java-based library that supports software transaction memory. Clojure supports STM, but other Java libraries also support STM. So one of them is Multiverse. And so GPars really gives a wrapper around it. You would still have to bring in the Multiverse libraries in if you want to use it. So to summarize, GPars is a library written in Java, but it really is written for Groovy fluency. So if you are programming in Groovy and interested in using concurrency and want to get into using actors or data flow or other operations, or simply just spawn threads in a thread pool, GPars makes your life a lot easier. That's all I have. Thanks.